In this lesson and the next, we'll tackle the issue of material selection in projects where strength is the determining factor. We'll start by describing how the approach is applied in this type of problem. Then, we'll go over the most commonly used indexes, and we'll wrap up with some practical cases. Most of the structures we use every day have to withstand stresses without being damaged. Think, for example, of a bridge that must not collapse, or the forks of a bicycle that have to absorb impacts. And then, consider the case of an airplane wing that must not fail. In all these cases, safety is dictated by strength. In design governed by strength, the main goal is to prevent structural failure of the component, whether that's a complete break or plastic deformation. This means that the stresses must not exceed a limit value related to the breaking strength or the yield strength of the material, which means that the most important parameter in this type of design will be related to the ultimate strength or the maximum stress that the material must withstand without failing. This maximum stress is an intrinsic property of the material, and it can be determined experimentally. It represents the stress beyond which the material fails, which can happen in two ways, either by the piece breaking or by it entering the plastic deformation range, resulting in the loss of its mechanical functionality. In the first case, we call it breaking strength, while the second one is called yield strength. Both of these parameters are measured as the force at which failure occurs, normalized to the cross-sectional area of the sample, and are typically expressed in megapascals. However, the stress conditions that a component may be subjected to can vary greatly from case to case, and may also involve very complex loading conditions. In any case, what is required in this type of design is that the maximum stress present in a component does not exceed the limit stress value related to the material's strength. Furthermore, failure can occur in different ways, depending on the type of material and the stresses to which it is subjected. For each of these failure modes, there is a specific resistance parameter, which we will now describe. The four main types of strength are tensile strength, which represents the stress at which a material breaks when subjected to tension. In brittle materials, such as ceramics or glass, failure occurs with small deformations. In ductile materials, such as metals or rubber, this happens after large elongations. Then, we have yield strength. This is the stress beyond which plastic or permanent deformations begin. It concerns materials that yield, like metals and polymers, but not brittle ones, such as ceramics, nor those that are highly deformable, like rubber. Next, we have compressive strength, which represents the stress that leads to failure under compression. Generally, it is high even in materials that are weak in tension. For example, glass, although extremely brittle under tension, can withstand compressive states well. Finally, we have fatigue strength. It is the maximum stress that can be applied to a material in the case of periodic loads repeated over time. It can also occur at stress values much lower than those measured under static conditions. Fatigue strength generally refers to a stress that can be applied and removed for 10 million cycles without the material failing. This means that, depending on the type of design, we need to choose the most appropriate strength parameter. In particular, we will refer to tensile strength in cases where the product is subjected to tension or bending and is able to withstand it without complete breakage. We will refer to yield strength when we want to avoid plastic, permanent deformation in a component, or when we want to ensure a greater safety margin. And we will refer to compressive strength when the product is mainly subjected to compressive forces, and to fatigue strength when loads are applied cyclically or repeatedly over time. The values of these four types of strength vary greatly from one material to another. Here, we provide a general overview of the tensile, yield, compressive, and fatigue strengths for the main families of materials. In all cases, metals, composites, and technical ceramics are among the most resistant materials, while plastics, rubbers, and foams occupy the lowest positions. Although the absolute values may vary, the hierarchy among materials remains similar for tensile, yield, and fatigue strength. An exception is the case of compressive strength in traditional ceramics and glass, which are brittle and weak in fatigue, but show high compressive strength. Finally, it's important to remember that in some cases, fracture or plastic deformation are not events to be avoided, but are actually design objectives. Fracture may be desirable in packaging or containers that need to be easy to open, as is plastic deformation. It can help with metalworking, or it can be important for those types of products that need to deform a lot without breaking. A practical example is car frames, which are designed to deform plastically so they can absorb the energy from impacts and protect the vehicle's occupants. In a design driven by strength, the approach to material selection still starts with translating the project requirements. Generally, when translating the project, the items will be organized like this. Under the function heading, you'll specify the type of product you're designing. The constraints will mainly concern strength, particularly failure, and the type of strength the product must withstand. Afterwards, any secondary constraints will be specified. The objectives will show the parameters that should be maximized, like the energy absorbed, or be minimized, like mass, volume, or the overall dimensions. Lastly, the project designer may work with some free variables, which could involve the choice of material or possibly the geometry of the product. The selection of the most suitable material, in this case as well, is based on defining the material's performance index. As in the case of design constrained by stiffness, being able to mathematically derive these indexes is important but not necessary. What really matters is knowing where to find these indexes, understanding their meaning, and knowing how to use them when solving problems. Here are listed some of the most useful indexes for this type of design, aimed at minimizing mass, costs, or bulk. For example, in the case of tension, we see when the cross-section is a free variable or for when there are no free geometric variables. Or for bending, we have the case of a free cross-section, that of a free thickness, or of a free width. For a more in-depth discussion of these and other cases, please refer to Ashby's texts or the dedicated sections of the Granta software. All these indexes have the same formulation, regardless of the type of failure. You will substitute the value for tensile strength, yield strength, compression, or fatigue depending on the type of failure you are concerned may occur. Material indexes, in addition to allowing us to rank performance, can also be used visually in multi-property graphs or bubble charts. Here we see the graphical representation of the material performance indexes presented in the previous case for a product where you want to ensure strength and minimize mass. The indexes appear as three networks, depending on the value of the index, with a slope of 1, 1.5, or 2. Or it shows as a vertical line in case you want to minimize mass without any free variable, or as a horizontal line dragged upwards when you want to minimize the overall size. We'll wrap up the first part of this lesson here, where we've explained the method for selecting materials in strength-constrained design projects. In the second part, we'll tackle a practical case and see how to apply this approach using different design strategies.